All right, first thing first, the Career Center has workshops. So the workshop is, okay, scroll down. Oh, okay, maybe not there. There's a PDF. Okay, save. And open. There we go. So the Career Center has May 2018 workshops in case anyone is interested. The first one is Thursday on the 3rd of May from 3:30 to 5 p.m. And this one is about managing stress and finding balance with mindfulness. So it's not really career specific. Anyone who takes my class probably can use this class. The second one is the career journey. What's next? Graduation, job search, or career exploration. Most of you are probably moving on to a 4-year university, so it may not apply directly to you. But if you do have time and you're on campus, you have 1 hour to spare, it may not be a bad idea to kind of check this out as well, because it might apply to part-time jobs. Whether you're graduating and job hunting or still exploring your ideal career and major, this workshop is for you. So just 2 resources here. Next one is Paid Internship California Intern Network Information Session. So anyone who's interested in internship, this one may be for you. All right, so let me open that too. There we go. So this one is on May 2nd from noon to 1 p.m. at Community Rooms 1 and 2. Find a paid internship with a public agency in your field of study. So they are not limiting to any particular field of study, so computer science is definitely one of those. Potential employers include Sutter Health, Caltrans, and the city of Sacramento. So kind of cool stuff. Most people do not think about Caltrans as a cool employer, okay? But I have one previous student who graduated from Sac State, I think either this year or last year, and he got a student internship with Caltrans. And one of his jobs was one of his responsibilities was to look into alternatives to controllers, really old and ancient controllers for traffic lights. So as it turns out, it's not easy because they want everything to be backward compatible, and they also have to make sure that everything can connect to the same network, and so that the traffic control stuff can continue to function with the new controllers. So that turned out to be kind of interesting because it's an application of MCUs, Arduinos, and Raspberry Pis, that sort of thing. But you cannot just say, oh, we can easily replace the old hardware with these things, because it has to pass all the tests, it has to be backward compatible, and it has to be shown in the field to be reliable. So kind of interesting stuff that you would not expect Caltrans to do, because hey, most people think about Caltrans as the people with hard hat and the bright yellow jacket on the road. Yeah, those are some of the employees, but they also have employees who have to be engineers. And this particular student that I have in the past is in the process of getting a professional engineer qualification, or I don't know how you call it. It's not a certificate, but once you become a professional engineer, your pay scale just go like boop, like that. It's one huge jump, once you become a professional engineer. The test, I heard, is really hard. It basically, in terms of difficulty, it exceeds the bar exam to get a lawyer, to get a JD. So lots of studying, okay, and lots of memorization and stuff like that. But to many people, it is worthwhile to get it. All right, one more. Transfer celebration. So I'm not sure how many of you are transferring and you're thinking about going to this particular activity. So this one is on Monday, May 7th from 5 to 7 p.m. Community rooms 2 to 4. So once again, it is on campus in the student center. I definitely cannot make it because I teach during that time. The Monday, Wednesday, assembly programming class. It starts at 7 o'clock, so I probably can make it, but then I'll be eating too much food and I can't teach at 7 o'clock anymore. So, but if you guys are transferring, that's one of the things that you might want to consider. Okay, so are there any questions about these 3 announcements? No. Is that useful? Or is it a waste of class time? Maybe useful, right? Some of these may be actually useful. Okay, cool. All right. So on my tabs, I got 3 things that are kind of interesting because I want to demonstrate a sample program. I will do this first, business first, and then we'll go for leisure, which is watching me hack the program that I started last in the previous class. So we'll start with all the good stuff first, okay? So the first one is Johnny, the second one is Jerry Ryan, and the third one is Peter Capaldi. Okay. So now we'll write a program to use all of these 3, okay, and it is related to your homework assignment. So we'll pull all of these things together to something that actually matters to you. All right, so let me close some of these other tabs so they're not distracting me. Okay. All right, so we'll start with the mousepad. In other words, we're going to start with a C program, and what we'll do with the C program is to illustrate a concept that you will need to understand to get the new lab done. Okay, so the early lab people have already started with this one, so the late lab people will basically get started, in an hour or so. Okay, all right. So I'm going to start with this. Okay, uint8 underscore t, the return type. This one is Johnny. Okay, and Johnny is going to return 5. Makes perfect sense if you know the movie Short Circuited. Is it just, yeah, Short Circuit, I think, not Short Circuited, it's Short Circuit. If you have not seen that movie, it's worth watching. It is one of the earliest movies that talks about AI, by accident, that sort of thing. It's really kind of cool. The second one is Jerry, for Jerry Ryan, the actress who played 7 of 9. So this one's going to return 7. And then the third one is Capaldi, or Peter. So Peter Capaldi, being the 12th doctor, is going to return 12. But I'm not going to say return 12. So I'm going to say return Johnny plus Jerry. Is that okay? All right. So now we have the usual main, okay, int main. And in main, we allocate a local variable. Okay, we have done this many, many times already. And the idea is, hey, we have to make use of the return value of Peter, put it somewhere, and then get rid of it. Is that okay? So this program is going to resemble, for those who are in the late lab, it might seem like, what is this program doing? Well, when you look at the assignment for this week, then you'll realize, why this program is actually relevant. I'm not giving away everything that has to do with the assignment, but I'm going to give away some of the kind of really crucial parts of the homework assignment. Okay, so are there any questions about this setup? I'm missing a pound include to deal with the uint8 underscore t for the program to compile. But other than that, is there any question why local variable x on line 19 should end up having a value of 12? No questions? Okay. So we're going to look into the assembly implementation of this code. So I'm going to start a new mousepad that is next to this one so we can look at both the assembly code and the C code at the same time. Okay, so where is the other window? There we go. Okay. So we'll deal with the easy ones first. Johnny, okay? So when you define a subroutine in assembly, you just start with the name of the subroutine as the entry point. Johnny does not have any parameters, so that means the return address is the only thing on the stack, and it is pointed to by the stack pointer at the time. To return a value of 5 is pretty easy. LDI A5, because return values are always going through register A, and we are now ready to return. So we do a LD, a load into register B, whatever the stack pointer points to, because the stack pointer currently points to the return address. So we put the return address in register B, increment D to deallocate the return address, because we don't need that anymore. And then we just do a JMP to B, because B has the return address. So I just want to copy register B to the program counter. So are there any questions about Johnny, which returns a constant of 5? There's no computation whatsoever. We just want to say, okay, let's return a value of 5. Is that good? Okay. So on top of this, I'm going to do something really strange. Okay. On top of this, I'm going to say, let's trash the other registers. So I'm going to put some random values into register C. It's like, and put some other random values into register C. Oh, C, A, B, C, D. Okay, so that's the only one I can mess around with, because we got A and B utilized. D is the stack pointer. So C, I'm just trashing the register C for no particular reason. Because, hey, guess what? The call subroutine can trash any register. Is that okay? So the convention is that the caller cannot assume a called subroutine to preserve the value of any of the registers, except, say, for the stack pointer. Yep?
So is that like relevant when you're in Peter?
When you're in Peter, then you have to say, can I put this into a register? No, you cannot count on that. So we'll get to that part. So you're absolutely right. You know exactly where I'm going. Okay, cool. So now we have Jerry. Okay, so Jerry is going to return a value of 7. Okay, basically the same stuff. So I'm going to do a LDI, C with something else. Okay, like 17. LDI A, which is the return value. In this case, it is 7. LD B with D, increment D, JMP B. That's it. Okay, that's Jerry. So now it is time to deal with Peter. Okay, Peter is the sum of the return value of Johnny and the return value of Jerry. Okay, so how do we do it? Well, we have to call the subroutines. So when you call a subroutine, it doesn't matter which subroutine you're calling, where you're calling from, the convention is identical. If there are any parameters, push the parameters first. If there are no parameters, or you're pushing all the parameters, then you push the return address. Does that make any sense? So in this case, I do not have any parameters, so I just go straight to push the return address. So I'm going to do LDI, okay, which register I use here doesn't really matter. I could use register A, I could use register B, or I can use register C. The only register I cannot mess around with, with this one is register D, because that's the stack pointer. So I'm going to say Peter return from Johnny. Okay, I'm going to preserve the order from left to right. Decrement D to preserve the space for the return address, and do it SDDA to actually push the return address. So push return address on the stack, and then we do an unconditional branch to Johnny. And then the label of Peter return from Johnny is going to be defined here. At this point, if I had pushed any parameters, this is the place to deallocate the parameters. But since in this case, Johnny does not take any parameters, there's nothing to deallocate from the stack. The called subroutine is already deallocating the return address. So that means right at this point on line 22, the stack should be balanced already. Is that okay? Yep.
So you said the caller cannot assume that registers are preserved?
Yes.
But so there's an intermediate return from
Johnny.
yeah.
Mm-hmm.
So in that case, we're going to be able to assume though that register A has
Well, so let's think about this, okay? So I'm going to make the mistake of thinking, oh, okay, because the return value of Johnny is in register A already, and I also know that when I call Jerry, Jerry is going to have its own return value in register A. So I'm going to copy register A to some other register so I can do the add later. So it's a mistake, okay? I'll do a CPR BA, and in the comment I say save return value of Johnny. Okay, mistakenly thinking that I'm save, I'm now going to call Jerry. Okay, so calling Jerry is kind of the same. Load A with Peter, return from Jerry. Decrement D, allocate a space for the return address. STDA to actually push the return address. And then we do a jump I to Jerry in this case. Peter return from Jerry is going to be defined here. So the first thing is, because I have two function calls, even in the C code, you can see there are two actual function calls. Each function call has its own return address. Is that making any sense? If I were to call Johnny twice, it would still be two return addresses, because each call, each invocation needs its own return address. Okay? All right. So at this point, I have no parameters to deallocate, which is really cool. And register A now contains the return value of Jerry. Does that make any sense? Okay. So now I can say, oh, okay, my own return value is really just the sum between register A and register B, because I saved the return value of Johnny earlier into register B. But that would be totally mistaken, right? Because if you look into when you look into Jerry, the subroutine Jerry is going to mess around with register B. Register B ends up with the return address. It's not the return value of Johnny anymore. Then go like, okay, maybe we should use register C. So go back here, and we use register C. It still doesn't work, does it? Because I intentionally put in one useless line of code to trash register C. Why? Because I can. In other words, you cannot count on a subroutine to save and restore any of the registers. Making that assumption is not going to work. Yep.
So would we need to then save the value in D?
In what?
In address D?
I think you got the right idea. You just did not articulate what you meant entirely. Okay, but it's a good start. Yep.
So we cannot assume that registers are preserved, but we can, correct me if I'm wrong, we can assume that functions that return values will have that return value in A?
Yes.
Okay.
So the return value of a scalar, the return of a scalar value being in register A is the convention between the caller and the called subroutine. It is also a convention that you cannot assume any of the registers being saved. So register B and register C, even though they are not the return value, you cannot assume those registers are preserved by a subroutine. Okay? And then register D is our stack pointer. Can't mess around with that one either. Is that okay? Yep. Yep, so we just push it on the stack. Very good. Okay, so I still need to save the return value of Johnny, because otherwise I will lose it. So the only way that I can do this is to decrement the stack pointer and then do a STDA right here. So I'm saving the return value of Johnny, okay, but not into a register, because registers can be trashed or overwritten by a called subroutine. But if you save it on the stack, then no one is supposed to mess around with it. Is that okay? So that means by the time Jerry returns and I need it back from the stack, I just have to pop it, okay? In other words, this part here is equivalent to push. It's pushing the return value of Johnny on the stack. When I need it back, I just have to pop it back into a register. And I can choose whichever register, except for register A, because register A right now has the return value of Jerry. So I can pop it into register B, I can pop it into register C, it's my pick. So to pop is exactly the reverse of push. In other words, you look at these two instructions and you are reversing the direction of each instruction, but you're also reversing the order of the instructions themselves. So if it starts with a decrement, then you end with an increment. And if the second operation was a store, you reverse the direction and you use a load. So in this case, I can use a load B. I could use C2. I'm just choosing B in this case. Doesn't really matter which one. So by the time we get to line 32, I would have the saved return value of Johnny in register B. The return value of Jerry is still in register A. I got the two return values. I can just add them, right? So we just do an add AB, adding the return value of Jerry. Excuse me, the other way around. We are adding the return value of Johnny, which is in B, to the return value of Jerry, which is in register A. And because my own return value is supposed to be in register A, after this add, I'm done. I'm done with my own return value. So the only thing left at this point for Peter to do is really to go back to the caller, okay, to resume execution in the caller. So to do that, we just do another LDBD, okay, but this time we are retrieving the return address, increment D so that we are deallocating the return address from the stack, and then do a JMPB, the typical return sequence of instructions. I mean, this is really, really typical. Yep.
Didn't you store Johnny in register C?
Hmm?
Because you added A and B, but I thought that you stored the value of Johnny in register C in line 22.
That wouldn't work.
It's not add AC
On which line?
on line 32.
Nope.
So what does line 22 do?
Line 22?
Yeah.
It's commented out now because it doesn't work.
Okay.
Yeah. I already explained why it wouldn't work.
Asking,
Well, that's because he walked in after I talked about that. But that's the nice part about having everything screen recorded. You have a free time machine. So are we cool so far with this? All right. So now we can write main. Okay. So to deal with main, I'm just going to do I'm going to run this program. Okay, to make sure that it does work. So I'm going to do a JMPI to main first. So this way we can actually kind of preserve the order of the definition of the subroutines. So main is going to be here. The first thing we do is subdd to initialize the stack pointer. And then we decrement D to allocate for local variable X. And then we just have to call Peter. Okay, so we call Peter right here. Peter does not use any parameters. So the only thing I need to push is the return address. So this is main return from Peter. The next thing is to decrement D to reserve a byte on the stack, and then do stdA to save the return address on the stack, and then the JMPI to Peter to continue execution in the subroutine, and then we put the return label here. Main return from Peter is defined here, so that when Peter is done, we come back to this point. So at this point, we have the return value in register A. Yep.
So you did the sub DD. Is that just to make sure that?
Yes. Sub DD is not exactly. Yeah. Sub DD is not necessary because register D starts with a value of 0 when we reset the processor. But to emphasize that the stack pointer really should be initialized before the program, I just put it here to basically emphasize the necessity to initialize. Okay, so after we come back from Peter, register A has the return value of Peter. Register D is now pointing back to local variable x. So to store the value is a store to whatever D points to with A. So that will complete x equals to Peter. And then after that, we are at the end of the entire program. So the local variable x is not going to be useful anymore. So increment D will deallocate the local variable. And then at that point, the stack pointer should be back to 0. And because main has no place to return to, we just say halt so that we can identify that the program has now finished. Yes?
If main has returned 0, we don't have, do we just load a 0 into A? Or
No, because nobody is actually utilizing that return value. So in C and C++, you cannot just say return. The compiler is going to complain and say, what value are you returning? But in assembly, in the context that we have here, there's no one to actually utilize the return value of main. As a result, I mean, you can, if you want to be more, to be more consistent, you can do LDIA with 0, just to specify, the return value of 0, but it's not going to be utilized. Yeah. Mm-hmm.
So if we don't do that at the end, we should have 12 in A, right?
Say that one more time.
If we don't do that, we should have 12 in A, right?
That is correct. A would still have the return value of Peter at that time. Yep. Yep.
So I've been messing around with it, obviously, because it was an earlier lab. So how does the return from parts run after the jump? Like, because I was not really understanding. We loaded up earlier, so why does it run after we jump?
The magic is here. Well, these 3 instructions combined is why the return is why it will continue at this label. Okay, so when you continue, when you do a jump I to Peter, it would just kind of blindly go to wherever the Peter label is defined, which is like earlier, right? But at the end of the subroutine of Peter, okay, assuming Peter doesn't mess up the stack, okay, at the end of Peter, okay, let's go up to Peter. So at the end of Peter, okay, all the stuff in between doesn't really matter. What does matter is at the end of Peter, we got these 3 instructions. So what these 3 instructions will do is it's going to look at the stack pointer, which should be pointing at the return address, right? So we put the return address into register B, increment the stack pointer, which is really just bulk keeping, making sure the stack is balanced. And then so the magical part is jump B. Jump B is not a jump I instruction. It doesn't go to a particular place all the time. It is not static. Instead, it will look at register B and say, whatever register B has, it would put it into the program counter. In other words, you are directly telling it where to go to based on the value of register B. But because of the way we initialize the stack, not initialize, but because of the way we push the return address on the stack, B actually has the return address, which means the jump B instruction on line 36 is going to continue execution where the label is defined, which is 45, line 45. Now, line 45, technically speaking, is not an instruction, so it will continue execution over here.
Oh, okay, thank you.
Yeah. Yep.
This wouldn't work, right? Because you need like a jump I main at the start, or you need to have main at the start?
I did have a jump I at the very beginning. Yeah, I believe so.
Okay.
Yep. I sneaked that in. Okay. So are we cool with this program? Okay. So now it's time to run it with some kind of a trace, because we want to double check and make sure things on the stack does look okay. So we'll do a Control A, Control C, and then go to the assembler. Okay. I really need to bookmark the assembler because it's used so often. Okay, so Control V, paste the program, let it finish compiling or assembling. Okay, all done. And then we go to the RAM file. Oh, there are errors. Okay, I missed something. Oh, okay. The rest of this program is there's leftover stuff here, so I need to kind of remove all that stuff. Okay, there we go. And here I was so excited, thinking it was a difficult problem to solve. Shucks. Okay. All right, so now we don't have any errors. So we go to File, Download as CSV. Let's call this Peter. And then we go to LogicSim. Let's start up LogicSim with one of these guys. And then load the processor. And we'll specify stuff to log. Okay. So typically we log the program counter, we log the stack pointer, and we also want to log a few memory locations. So when you decide how many memory locations you should be logging, we really should think about how many stack positions will be used. Location 255 is our local variable x of main. Okay, so that's going to be consumed. Location 254 is the return address back to main. Location 253 is the return address of Johnny. It's the return address back to Peter from Johnny, which will also be used for the saved return value from Johnny. So it's going to be double purposed. So we should see location 253 being overwritten twice. The first time overwritten with the return address to Peter from Johnny, and then the second time is it will be saving 5, which is the return value of Johnny. And then location 252 is going to be the return address from Jerry back to Peter. Okay? So those 4 locations on the stack should be used as far as I can count. Is that okay? Before we do that, I just want to double check that I did deallocate the return value of Johnny from the stack, because I may have forgotten that, but I want to double check. All right, so let's see. Nope, I did deallocate it. The increment D is deallocating the return value, the saved return value of Johnny on the stack. So everything should be balanced. So we should log 5 locations because we know exactly 4 should be used according to my calculation. So I'm going to log 5 just to be sure, just in case I miscount something and go like, oh, 1 more location is being used. I need to explain that now. Okay, so switching back to LogicSim and going back to this window, we go to RAM, which is here, and we'll go log the last 5 locations. Okay, so we have, okay, in which order do you guys want it to log? Do you want 1, 2, 3, 4, 5 or 5, 4, 3, 2, 1?
No, 5, 4, 3.
Okay, all right, 5, 4, 3, 2, 1. Can we leave those as binary? I think it's a good exercise. Leave those as binary, and when needed, we'll convert those to hexadecimal. Okay? Because this way I don't have to go back and change the radix for each one. I'm just being lazy here. All right, so now we want to save the file, okay, save the log to a file. And we'll call this peter.tsv, or tab separated value. And then we can close this window. And don't forget to actually load the program. So we want to load image. And it's called peter.csv. And here's the program. All right, so I think we're ready to go. Did I miss anything? Okay, all right, so let's go ahead and Control K, and it should be done at this point. Control K again to stop this, the simulation. So the first thing I'm going to check is really just to look into the content of RAM and look at the 5 locations. And the first thing I'm going to check is local variable x, okay? Because if local variable x is wrong, then I know something is really wrong, okay? So which location is corresponding to local variable x? The last location, right? Location 255 or FF? It does have 0z in it, which is 12, okay? So that's good. That gives me a pretty good feeling. But I still want to double check the rest of stuff on the stack. Knowing that the toy processor does not have an interrupt mechanism, that's the only reason why I can kind of go back and check the content on the stack after the fact to see whether the program executed correctly. If your processor or microcontroller unit has interrupt mechanisms and there's only one single stack, then you cannot look back onto the content of the stack and say, oh, I can look at the trace left behind and figure out whether the program worked correctly or not. Because the interrupts would have destroyed the content on the stack in a way that you cannot really predict. Does that make any sense? Okay. All right. So this is the return address from Johnny. From Peter back to main is 2C. So we can check that. Okay. Just because it looks like a return address doesn't mean that we can just kind of let it go and not verify. So we can go to the assemble tab and then scroll down to main, and then we double check this location and ask, is that location 2C? And as it turns out, it does match location 2C in hexadecimal. Cool. Going back to the log here, this is the return value of Johnny. But remember, this is overwritten. Okay, so this location, which is corresponding to 253, is overwritten twice. The second time we overrode it with a value of 5 because that was the return value from Johnny. This becomes the return address from Jerry back to Peter. Okay, and it's 1E. So we want to double check that. So we switch back to the spreadsheet and scroll up. And we look up this label, Peter returned from Jerry. It is 1E. Was it 1E in memory? Yep, it is 1E. So everything does match what I thought they should be. One more thing that I can check in the simulator real fast is whether the stack stayed balanced or not. So for that, we have to go to the register bank, look at register D. It does have a value of 0, 0, so the stack pointer itself is balanced. So everything looks good at this point. But what do you think the trace is going to look like? The interesting part is location 253 should be overwritten twice. It should be updated twice. So we're going to look for that. Okay. My personal preference is to use the assembler to do it, or to use a spreadsheet to do it. So we can go to, should I go to any? Yeah, go to a subfolder, and with this one, we'll go ahead and import the content from a TSV file. So we go to File, and we go Import, and Upload, and it's called peter.tsv. And then click the last one to know, and I think we want to replace current sheet. I think that will work. And import data. There we go. Cool. So this is location 255, 254. This is 253. We should see it updated to the return address first, and then it will update to 5. So let's scroll down. This is the return address. The return address in hexadecimal should be a 16. So now the question is the label Peter returned from Johnny 16 in the assembler? Okay, we can check that. So we just have to scroll up a little bit from Johnny. So this should be the one. And it does have a address of 16. So that's the first time we overwrote the location 253. The second time we overwrote that location is when we saved the return value of Johnny, which is 5. So we go back to the log, and then we scroll down a little bit more, and you can see how it is overwritten, just a little bit up, right here, to exactly 0.5, which is the return value from Johnny that we are saving on the stack. So by analyzing the log of the execution of this program in Logisim, I can double check and verify that the program is working. Now, obviously, when the program is working fully, I could have just looked at location 255 and say, yep, everything is good, without actually going through this process. The chances of you guys writing a program that works the first time is not 0, but it is not likely either, okay? So that means you will probably encounter a program that doesn't do what you think it should do, at least in the first time. How are you going to debug your program?
That's one thing when we were making the programs, that was like, it was really hard to try and run it multiple times because every single time we had to make a whole RAM file and then load the file.
That means you should extract as much information as possible from the log. Yep. Well, at least you don't have to turn in a job and wait for the job to come back the next day. Nor punch cards. Yep, so from that perspective, your development tool chain is superior to a lot of tool chains back in the 60s. But I do understand that it is a lengthy process, okay? But that means, that really means that you really need to analyze the trace as much as you can so that you can figure out what the problem is, then you go back and fix it. It goes really against RAD, RAD, which stands for Rapid Application Development, as well as the current trend of using IDE so that you can just make some changes, run it again, make some more changes, and run it again. This doesn't lend itself to that sort of development model, which is a good thing or a bad thing. But what do you think? Depends on the circumstances. I like that answer. In the case of actual production, it is not advantageous. In the case of learning, it is advantageous because it really forces you not to use maybe this random change is going to fix the program approach. That is not going to work with a tool chain this inefficient. Is that okay? And trust me, this is not really that inefficient. I have developed software using even fewer resources. Try a single LED. There's a circuit board. You're not uploading your program. It's not even right-clicking and say load image, okay? You are taking your actual EEPROM. Remember we talked about EEPROM, the kind of chip that has a window on it? You take that chip, you take your file on a floppy disk to a station somewhere in the company. You plug in your EEPROM onto a special programmer thing. You push in your floppy disk. You run a special program to program the EEPROM so that the image is now quote-unquote loaded onto the ROM. Then you go back to your own cubicle. You put the ROM into the ROM socket. You power up your microcontroller. And then the only thing you can observe is whether a single LED is lit or not. In other words, did you get to that part of the program or not? If it doesn't get to the part that you think you should be getting to, then you'll be staring at the source code to try to figure out. Because every single time you make a change, you have to go through that process again.
Like
and then,
CLs.
it is. And then for every 16 ROMs that you overwrite, you have to you now have a tray of 16 of those EEPROMs. So you take the 16 EEPROMs because that's all the company has, to a UV ultraviolet eraser. You put it in. It's kind of like a toaster oven, except it uses ultraviolet. So you put these 16 things in, you slide it in, you turn on the timer, which takes about 15 minutes to erase the EEPROMs. So during those 15 minutes, Now you have time to truly reflect on your coding style. And ask you, why is this the 6th time I have done it in one single day? So I would say this is far more advanced compared to a single LED. And you might still get into a situation where you have to use that approach. I mean, it's not likely anymore, but you might actually get into it. Okay, so anyway, this sample program is all done. Are there any questions about the C version versus the assembly version? Because if there are any questions, now is a good time to ask before we move on to the entertainment part of the class. Or infomercial, depends on how you look at it. Any questions? Any questions about the concept? Any questions about the instructions? Any questions about how the stack is utilized? No questions? All right, well, I'm going to assume that there's no question. Yep, go ahead.
If there's like an array, for instance,
Uh-huh.
just be returning like an address to the array if any changes are made.
Okay, so you're asking about a different program. It depends on what are you returning. Depends on the C code. So if your C code is returning, there's no way for a C program to return an array, because an array is no more than a pointer. So when you quote unquote return an array, you're really just returning a pointer to something, integer structures or whatnot.
So would it store all of the elements on the stack?
Nope. It depends on what the code is doing. Are you returning an array that is a local variable, or are you returning an array that is passed to you as a parameter? Which way?
So would it put elements on the stack when you have like a for loop that's putting elements into the array?
No. Okay, so I'm going to show you something that's really bad, but people do it anyway. Okay, so here's an array, and a function that returns a pointer to an integer. So I'm going to call this array function, and it has its own local variable, which is an array of integers. So we have int r, I don't know, 16. Okay, doesn't matter what it is. You do something with your r, and then when you return r as a parameter. That is completely valid syntax in C as well as C++. Okay? All right. So now you have another function that makes use of this, right? So let's say you have void subroutine, and this guy is going to make use of the return value from the other one. So it has int star return value, and then we say return value equals to array func, like that. So return value now is quote unquote initialized to an array, right? Or so we think. So when we say something like this, okay, what is that going to do? Stack-wise. Yep.
So isn't like the thing that you're returning from array func only locally allocated, so shouldn't that have already been popped off the stack by the time you
Yes. So by the time you get to line 35, the stack pointer is already pointing to above the address of return value bracket 0. Does that mean this is going to have a problem? Does it mean that this code is going to crash? Absolutely not. It is just using a part of the stack that is currently deallocated. The portion of the stack that is deallocated can be used by interrupt surface routines. So that means whatever you put here may continue to exist as is, or the interrupt can change it. You have no idea whether the interrupt is going to do it or not, or when it's going to do it. So that means this code, depending on the timing of your interrupts and the nature of the interrupts, and depending on how the interrupts can stack up and so on and so forth, This code may work for a whole year, and then suddenly it just crashes. It may crash every month in a different way. Because a different interrupt kicks in, it overrides this location with a different value, causing the program to completely crash in a different way. Those are really, really difficult problems to deal with because it is not reproducible. And every single time the problem happens, the symptom is entirely different. And it is not deterministic. It may not happen for a year, and then suddenly it starts to happen every single week or every minute. And then it stops happening for 5 years. So, but do you guys understand why this is really, really bad programming style? Okay. So, is that answering your question? Okay. All right. All right. So with this all done, we got about half an hour left. So it's time to go back to the program that I was trying to illustrate the other day, which is the hacking part of this program, which I still have here. It's called hacked1.stripped. Okay. So we'll go back to this one and we'll try to hack it again. So just in case you have forgotten what the program does, it checks a password. If the password matches, it will say, yep, now you have access to the full feature of this program. If the password does not match, it just says, read the Fine Digital Millennium Copyright Act, which is, look it up. Look up DMCA and understand what it is, because it is relevant to anyone who writes software, especially people who have to kind of occasionally deal with copyright protection, circumvention, and stuff like that. Okay. So the idea is I want to hack this program so that it would allow me to get into the full feature portion of this program. Is that okay? All right. So because it is reading a password, a hacker may think, maybe if I enter a really, really long password, it would cause the program to crash. Okay, so you try a longer password, doesn't crash. You try a even longer password, it still doesn't crash. So typing a password like this, is not really a good way because it is just not very efficient. So one way to do this, okay, and this is not very systematic, but it is close enough. Okay, this is what I had worked out already. So we'll start with something new. Okay, so it is usually best to do something that has as little repeatability as possible. And there are ways to generate sequences of characters that do not repeat. Okay, I'm just counting on chances here. I'm just a single monkey with a single keyboard. That's all. Okay, and that's Shakespeare. You guys know what? Yeah. Okay. With enough monkeys and enough keyboards, monkeys can write Shakespearean plays. That was the idea. Okay, so now I can run the program again, but this time I'm redirecting, so I'm not typing anything. So I would use that file to serve as standard input. So this way I can repeat the experiment easily without having to type a whole lot of stuff consistently. And it has a segmentation fault. Woohoo! I crashed the program. Because being able to crash the program means the program did not anticipate certain things. Okay? When the program doesn't anticipate certain things and the input is just kind of random, it just crashes because it is going to a location where it cannot continue execution. But that also means that I might have a chance to gain control by specifically specifying that password file to a certain pattern. Okay? It gives me a chance of hacking this program. So the first thing I'm going to do is to rely on my BFF GDB, okay, and run it inside GDB. Same test, password, but this time it's in GDB. So my BFF says, oh, not only is the program crashing, let me tell you where it is crashing. Now that is really relevant. It's really helpful because with a processor like the i5 processor that is running in protected mode, it actually is pretty smart. Okay, it will say that, oh, this instruction is attempting to do something that is not what it is supposed to do, I'm just going to give you a segmentation fault so that we are not going to execute that instruction. But GDB goes one step further. It will tell me which instruction is responsible for the segmentation fault. So I'm going to use a GDB command called examine, X for examine. I is standing for instruction. And then $RIP stands for the instruction pointer. The instruction pointer is really the same thing as our program counter. It is basically saying, oh, the processor is now trying to execute that instruction. That's the address. Okay, it's the program counter. So this entire command in GDB is basically saying, show me the instruction that the instruction pointer is pointing to right now. Because it has just gotten a segmentation fault, this is the instruction that is responsible for the segmentation fault. This is where it is crashing. Press the Enter key. It says it's a return quad. Okay, RETQ stands for return quad. A quad is basically a 64-bit number. Okay, 8-bit number. I mean 8-byte number, which is what you need to specify a return address when you have a 64-bit architecture. Okay, so it says I'm attempting to return to a location that is not good. And it uses the same mechanism that we use in our toy processor. In other words, it is using what the stack pointer is pointing to as a return address, exactly like the way we do it in this class. So where do you think I should go next? If I'm a hacker and go like, how can I gain control of this program? Where should I go?
Up or down from that address point?
The stack pointer, right? I need to look at where the stack pointer is pointing to and a few bytes above it too. Okay, so we'll do that. So we'll do a x/, because it's only 8, and return address is 8-byte long, so I will print 8 of those things. Each one is a byte, and I'll print it in hexadecimal. And this time I would use RSP as the location, the stack pointer, okay, which is our register D. It goes like, okay, this is my return address. When you look at this return address, does it look really random to you, or does it look suspicious? And if it looks suspicious, how is it looking suspicious? These are all hexadecimal numbers. So now the question is, does it correspond to anything in the password file that I gave the program? These are all ASCII codes. Very good. Okay, so these are all ASCII codes. I can recognize this is a digit of 0. This is lowercase a. This is 9 as a digit. This is 8 as a digit. This is 7-3, which is 14 characters after A. Okay, so A, B, C, D, E, F, G, H, I, J, K, L, M, O, P. I think it's a P, right? Huh? That's an O? Okay. So O, and that's a D, that's a F, and so on. Yep.
You're just gonna like look in that text file and for that set of ASCII codes to change it to whatever address you want for returning or something?
Well, I know where to change. Okay, so I know which part of the password file will give me control over the return address. Okay, so that's the first part of the puzzle. There's another piece to the puzzle. So I'm just going to write this down on in someplace in Notepad. Okay, so I'm just gonna use this. Okay, so I'll just kind of copy and paste it into here. All right. And I just say, okay, fine, I'm done with the GDB at this point. I go back to the test file, the password file, and this time I'm searching for that pattern. So the pattern that I'm should be searching for is 0A98. That's an O, and then we have a D, F. What else? D, F. Oh, that's a 7-5. 7-5 is 2 after O, so Q? PQ, right? Okay. So I'm looking for that particular pattern. Okay, so let's put it over here. And then in VI, I can now search for 0A98OD. Oh, okay. 0A98OD. there's a SDFU. Okay, so I probably just miscalculated the ASCII code because that's the only occurrence of a 0A98. Okay, let's search it one more time. Yep, so that's the only occurrence of that. Is that okay? And it has 8 bytes, so I'm going to go, okay, this is the first one. Okay, so we will go 1, 2, 3, 4, 5, 6, 7, 8. So from here on, this part of the password file is not useful because, the return address are these 8 bytes. So these 8 bytes will give me control to where I want it to return to. Is that okay? In other words, I have now hijacked the steering wheel of the bus. Not to be confused with bus fight bus, but this is a different bus. Okay? So now my next question is, how do I want to steer this bus? Because right now the program is just crashing. Okay? Some random thing is steering the bus and the bus is just falling off the cliff. I want it to go in a particular direction. So the next thing we need to do is to use the only clue that we can get from running the program correctly to find out where is this, okay? Because if you think about it from the perspective of a programmer, it probably has some kind of a conditional statement, right? To check whether the password is correct or not. If the password is incorrect, go here. If the password is correct, go somewhere else. That's my assumption. Is that a valid assumption? Reasonable assumption? Okay. So I now need to go into the program and say, where in this program is printing RTF DMCA, exclamation point. Okay. So a quick and easy way to do this is to use a program called Hex Dump. So Hex Dump -C, and then you give it any file. It doesn't even have to be executable. You can give it any file and it will dump everything in ASCII code to you. I'm piping it to less just so that I can search and I can page up and page down. So the output looks like this. And then we just look for DMCA, okay? The fewer characters, the better. So I found that string. Cool. Because this gives me the offset from the beginning of the executable to the part where it says, oh, this is the string, okay? It is at offset 670 from the beginning of the executable. Okay, so I'm going to write that down, okay? 670 offset to DMCA, RTF DMCA, exclamation point, okay. But I don't know where the code is, okay? I know where the string is, but I don't know where the call to whatever function that is supposed to print it is. So now I need a different tool. It's called Objdump for object file dump. And I want to disassemble the code. I want to kind of look back from the executable, which only contains the opcode, the binary opcode stuff. And the disassembler is just looking at those opcode and reverse everything back to mnemonics so that I can actually have some idea of what is going on in the program. Okay. And I'm going to pipe it through less again, just so that I can page up and page down. So the first thing we notice is everything is off by a certain amount. If you look at it, everything in this file are 400 blah blah blah. Did we see something like that earlier? The instruction pointer. The instruction pointer had a value just like that. Okay, so the entire program is loaded into that specific place. So specifically, we're looking for the offset of 670. So just looking for it. Okay, we found exactly one occurrence, which is here, that specifies 400670 is putting into a register, and then the next line identifies as a call to put S. Put S is put string, which is a C, not C++, but it's the C way of outputting a string to standard output. It's basically the same thing as C out, less than, and then whatever the string you're passing it. Okay? So that gives me a pretty good clue of, hey, this is where it is printing RTF DMCA exclamation point. Is that okay? If you're not sure about this, we can change the message to double check and verify that this in fact is that address, okay? But it is. So now we go around this and go like, okay, let's look at the context of this code here. The first thing we notice is the instruction right above the move instruction here is a jump. That should be very suspicious to you, because if the previous instruction is an unconditional branch, how did we get here in the first place? Why would I end up at location 5BA if the previous instruction is an unconditional branch? Which means if the program is executing sequentially, it would have gone to location 25C, which is here. Why would I put any code here and expect it to execute? Huh? Because it's alternate. Very good. So that means we are in what kind of a control structure? An if then else. Okay, very good. So now the question is, where is the jump to go to location 5BA, 4005BA? Can someone find it? Okay, there's a JE, okay? This JE instruction is going to exactly that location, 5BA. So now we have found the structure of an if then else statement. This JE is branching around, it's going to one particular branch. If the JE does not happen, it's going to the other branch. So we have two branches. One is corresponding to printing the message that says, oh, sorry, your password does not match. What do you think the other branch is going to? It does match, right? Yeah. Okay. And if you look at what JE is really equivalent to our JZI. It's a conditional branch. It says if equal to, go there. Or if it is 0, go there. Okay? So it's a conditional branch. So now we kind of understand the structure of this code. If the password does not match, go to location 5BA. Location 5BA is going to print RTF DMCA exclamation point and exit the program. So now the question is, what if we did not execute what if the conditional branch did not happen? Then we'll be falling through. So when we fall through, that branch must be corresponding to the code to say, oh, your password does match. It's cool. Is that okay? And that address is listed right here. It's 4005AE. So I'm going to copy that. So copy, oops, okay. Click on the wrong window. 5AE, okay. We got 10 minutes left, so plenty of time. We'll get this. Copy. And then over here, okay, not this one, the other one right here. And we just do a paste here, just so that I can remember where it is. All right, so we almost got everything now. So the only thing that's left to do is to go into the password file and change the last 8 bytes to reflect that address. So now we go to VI, okay, and we go like, okay, so now how do we change these 8 locations so that it reflects the address of a bunch of zeros and then 4005AE? Well, you can't do that with a text editor. A text editor will only let you enter ASCII code or printable characters. But if you have like special characters like that, except for the 40, none of these can be entered using a typical text editor. Okay, so we'll use Hex Edit, okay, which is a really cool tool. So Hex Edit allows you, it's kind of like the reverse of Hex Dump. So instead of printing, this one allows you to change. So we go to the last few locations, which is starting with the 0, which is this one here. And then this time we have to be very careful, because the Intel processor is what we call a little endian processor. A little endian processor, EN, not IN, a little endian processor means the least significant byte is at a lower address. Okay? In the address, AE is the least significant byte. The 05 is the second least significant byte, and then the 40 is the third least significant byte. So that means the 30 should now get the value of AE. The 61 should get the value of 05. And then the 39 should get the value of 40. And then everything else should be all zeros. Okay? So we just type it in. AE for the least significant byte, 05 for the second least significant byte, and then 40 for the third least significant byte, and everything else should be all zeros. Did I modify the right bytes? Yeah, I did. I was just looking at the 08 at the end. That's just a line feed character, so that's not a big problem. Yes, go ahead.
Is there a difference between inputting lower and uppercase characters, or?
Does not matter. It's just hexadecimal. Yes.
So you said E is the least significant bit, right?
AE is the least significant byte.
Oh, the whole thing.
Right. So when you read a number as a whole, the rightmost part is the least significant. But when you store a multi-byte thing into memory, it will take up multiple bytes. So now the question is the least significant byte stored at the lowest address or the other way around? So there's no right or wrong, okay? It's just a matter of what is the preference of the manufacturer. And Intel, is always little endian, and then Motorola is always big endian. So it's just a convention kind of thing. Okay? So now we have modified this thing, and we type Control X to get out. Control X, save yes. And now we try to run the program again. So we say, hacked, redirect from the test password file, and it says, welcome back. So we have now successfully hacked the program. We have just successfully circumvented a password checking mechanism. And it is fully legitimate because I wrote this program. You can actually hack your own program without being considered illegal. Yep.
Now, as far as programs go, how similar are they, the overall structure and method to, I guess, using this method? Is it at all similar or applicable for use of other potential programs?
So the way you do this as a hacker, or one approach, or the usual approach to do this, is you're looking for things that a careless programmer would make assumptions of. Okay, so let me put it into a kind of a better description. So let's say you're dealing with a protocol of some kind, okay? HTTP, okay? Interpreting the format of an image file, that sort of thing. Anything that has a standard, okay? So you're looking for something that has a well-established standard. So then you look into the standard, and you're looking for something that is both null terminated and length limited, delimited, okay? For instance, the comment field of a JPG file may fall into that category. So you read the standard. I'm not sure about this one, but I'm just making the assumption here. So the standard may say that the comment portion of a JPEG file is null terminated as a string as text, but it should be no larger than, let's say, 4 kilobytes. So you're looking for something like that, that it is by nature, most of the time it is null terminated. It has a particular character to mark the end. But at the same time, it is also having a maximum length that is defined. So a programmer, who is trusting, let's just say, will basically say, oh, okay, so in order to parse and make use of the comment, I'm going to allocate a 4 kilobyte buffer, and I'm going to use string copy to copy from the file or copy from the full buffer into this local array, and then I'll do some parsing, look for GPS locations, look for names or whatever, okay? Is that making any sense? If the programmer is trusting, the programmer is basically saying, oh, the null terminator will appear before the end of the 4 kilobyte allocation. Is that making any sense? Because that's what the standard says. And a trusting programmer has this assumption of people are playing by the rule. So it is safe for me to allocate an array of 4,000 bytes, and I don't have to check whether the null terminator is occurring before the end of those 4,000 bytes. Is that okay? So the hacker is making, is exploiting this trusting, programmer and go like, I'm going to break that rule. How are you breaking that rule? I give you a no terminated string that is longer than 4,000 bytes. So what's going to happen is if the program uses string copy instead of string end copy, it will continue to copy until it finds the no terminator. Okay? Which also means if your comment is 6,000 bytes long, it's going to overwrite not only the 4,000 bytes of the local array, it will also overwrite 2,000 more bytes on top of that local variable. And that's basically what we just saw. We just saw a case where the password is longer than the buffer allocated for comparing the password or processing the password in any way. So the excess portion of the password is overwriting a portion of the stack, and by controlling what content I'm using to overwrite the stack, I change the return address. So that is basically one approach of hackers when they want to break a program is they look for standards, they look for ways that someone can make an assumption so that a careless programmer or trusting programmer would use a string copy approach when they should be also be checking for the length. Is that okay? So as a hacker, they will be looking for standards of all kinds. Doesn't matter whether it is just HTTP or a JPEG file format, anything that has something that has this nature. It is no terminated or there's some kind of termination indicator, and on top of that, there's a maximum length allocated. When there's a combination of those two, you have a golden opportunity to hack into the program. Yep.
What about like types? So like say the program wants to take in an integer, but you feed it a string. Is that also stored on the stack?
That is typically not going to be a problem because most programs because it doesn't cause any overflow, it doesn't cause any issues like that. So it is not going to be likely to be hackable or to be a vector. For those of you who want to go like, nah, this stuff never happened. So you can look into GDI plus window exploit. And there's a full history of what that one was. And it impacted a wide variety of versions of Windows. And the vector is really kind of creepy because it has to do with the graphics library. And I think it has to do with the parsing of one particular image file. So in order for your computer to be hacked, all it takes is for you to go to eBay and go like, I wonder if someone's selling a SSD cheap, inexpensively. And you look, and there's an image of an SSD drive. If somebody is inserting that exploit code into the image itself, your computer can be hacked by just viewing an image from a browser. That was a long time ago, okay? They got it fixed already. But when it was discovered, it was a big thing because it was hitting not only one version of Windows, it was hitting a spectrum of versions of Windows. So it was kind of an interesting thing. You guys can look into the exploit DB and find out exactly what it was, how what kind of approach the hackers took to exploit this one. Okay. All right. So we're going to head out to the lab for the late lab, and then for the early lab, I hope the sample program is useful.